Hello, my name is Morgan Truitt, and today I'm going to be discussing electricity and magnetism. I'm going to break these concepts down into their definitions, discuss how they work together, compare the two, discuss some real-life applications for both, discuss induction with its utilities, and so without further ado, let's just go ahead and get started. So electricity can be defined as the flow or presence of electric charge. It's a form of energy caused by the movement of electrons through a conductor. A conductor can typically be seen as a wire. Electricity is the energy produced when charged particles move and can be either positive or negative. We know that electricity is used to produce things like heat, light, motion, sound, etc. So moving on, we're going to define magnetism here. It's the force of attraction or repulsion that acts between magnetic materials due to the motion of electric charges. It arises from the spinning and other motions of electrons inside of atoms. Another key trait of magnetism is that every magnet has a north and a south pole, with opposing poles attracting to each other and like poles repelling. So this would be like north to north would be, they would repel from each other. But north to south always attracts. So then how do these two end up like meeting each other, right? We end up with something called electromagnetism, which is when moving electric charges create magnetic fields. When an electric current flows through a wire, it creates a magnetic field around said wire. However, a changing magnetic field is able to produce electric currents. When a magnetic field changes near a conductor, it induces an electric current in that wire. So between electricity and magnetism, let's go ahead and discuss what's similar between the two. Both are able to attract or repel objects, but both are also caused by electric charges. Electricity can be caused by both objects at rest and in motion, while magnetism is only caused by moving charges. We'll hear more about that on the next slide. As discussed, when defining the two, they both produce fields of some kind, one being electric and the other obviously being magnetic. Both can also be created by one another, as addressed in the previous slide, and both are required aspects of electromagnetic force. So we heard about the similarities, and there are plenty of them, but they also have their differences. How these energies are produced can come from different sources. So an electric charge can be produced while at rest or in motion, whereas magnetism can only occur in motion. Additionally, the poles and charges differ between the two, with electricity only being able to be positively or negatively charged, and magnets are both positive and negative charges at all times. With that, electric flows start positive and end negative, but magnets are always in a closed loop, going from north to south and then returning back to north to repeat the process. So much like their sources, electricity is able to act on both stationary and moving objects, while magnetism can only impact moving objects. So just to better understand magnetism, here we have a real-world example of how it would look in medicine, right? A piece of medical equipment that would be an example of using magnetism would be a magnetic resonance imaging machine, also known as an MRI. These machines use powerful magnets and radio waves to create detailed images of the inside of the human body. A strong magnetic field aligns the nuclei of hydrogen atoms in the body, and then when radio waves are sent in and then turned off, the hydrogen atoms return to their normal alignment, which releases energy. So that energy is then detected by the machine and then converted into high resolution images of both organs and tissues within the human body. So within the assignment prompt, we were asked to calculate how many amps a common household item would use when operating at its given wattage on a 120 volt circuit. I opted to look closer at my desk lamp. This lamp has a listed wattage of 60 watts, With this and the pre-chosen voltage of 120 volts in mind, I was able to calculate how many amps this desk lamp uses by dividing the watts by the voltage. As you can see, this is 60 over 120, meaning the lamp draws about 0.5 amps of current when operating at 60 watts on a 120 volt current. So moving right along here, we're going to discuss electromagnetic induction. It can be defined as the process by which a changing magnetic field creates an electric current in a nearby conductor. The conductor would need to be placed near or within a magnetic field so that the field can alter the magnetic field of a wire, causing the electric changes in that conductor to move and then produce an electric current. So I felt that understanding electromagnetic induction, it was important to acknowledge the laws surrounding it, specifically the concept being discovered by Michael Faraday in 1831. He had established a law stating that the faster a magnetic field is changed, the greater the induced voltage. So we're going to go ahead and take a look into some like everyday applications or everyday examples of electromagnetic induction, right? So we might have something like an electric generator, which converts mechanical energy into electricity. And then there are things like transformers, which use induction to transfer electrical energy between circuits and alter voltage levels. An example found within a lot of households is an induction cooktop, which it uses magnetic fields to directly heat metal cookware, which obviously makes your food hot. And for the music enthusiasts, we have electric guitar pickups. The vibrating strings of a guitar disturb electromagnetic fields, which induces a current that turns into sound or music. The final example I'm going to give here is something most of us use all of the time anymore. It's a credit card reader. These devices detect changing magnetic fields from the strips within a credit card or debit card. And with all that information being said, I would like to conclude my presentation by saying thank you. I appreciate you for taking the time to listen to the information I gathered on electricity, magnetism, and those two concepts unified. Have yourself a good day.